Hey everyone, I'm Luke. This is my talk on cryptography from 500 BC to quantum computing, or the more popular title I submitted, which is Harry Potter and the Key of Encryption. So the keys end up being super important in what the story is all about. So I'm a Harry Potter fan, but I am not a crypto engineer. I'm a web developer who got into security. And I remember thinking I couldn't be a real security engineer because I was scared of crypto. So while I'm not a crypto expert, I've been using it a lot more in the last 3 years, and I found that learning some historical crypto really helped me to understand modern crypto. And so what I'd like to do today is cover crypto from about the Big Bang up until yesterday. So I'm going to go really fast. You don't need to take any notes because the slides are already up at speakerdeck.com/groovecoder, so just go check that. My hope is that a quick blast of all of this crypto helps you realize that today's crypto didn't spring out of nowhere, and it makes you a little more confident and comfortable when you're dealing with crypto. So there's two stories of cryptography that I'm playing out over time. One story is about technology, so this is like writing, telegraphs, radio, internet, all that good stuff. The other story is between code makers who turn plain text communication into ciphertext versus code breakers who seek to attack ciphertext and recover the plain text. So throughout this talk, I'm going to track this with a timeline that shows the ages along the top and the code making versus code breaking in the middle. And we'll spend a few minutes in sort of each age and with extra time in the computing age, and then we'll even get to briefly look at how quantum computing is challenging all of the encryption of today. But first, let's start with ancient code making, which happened with just plain old writing. So the first ciphers used in writing were simple transpositional ciphers. These are anagrams, right? And although it's simple to understand, they can actually be really strong. So for example, if you consider this short sentence, which has 35 letters that can be rearranged into 50 trillion possible permutations. Now when we talk about the strength of an encryption system and how easy or hard they are, we measure them by time complexity, which is basically how long it would take to break the ciphertext and recover plain text. So for example, if you have this anagram ciphertext and you could rearrange it once per second, it would still take you 1 trillion billion years to check all the possibilities. But we can't just send somebody a random anagram, because how would they know the correct plain text? What if they deciphered it to a false positive anagram with completely different meaning than what we intended? So what you need is a deterministic way to encrypt and decrypt anagrams. And this is how we get to algorithms and keys for encryption. So there's always a key involved. It's the story of this talk. One encryption algorithm for anagrams is called a rail fence cipher, and to use it, you write a plain text message like they are attacking from the north diagonally across some number of rows. In this case, it's 4. Then you go through each row and you write the letters from left to right, and you end up with this anagram ciphertext. So to decrypt it, the recipient would draw a grid of rows and as many columns as there are letters, of four rows. And then they would write the cipher letters across the grid diagonally to recover the plain text. So you can do anagram encryption with a machine. And the one we're going to talk about is called a scytale, which is actually thousands of years old, and it performs anagram encryptions. So to use it, you wrap a piece of paper around a cylinder, and then you write a message across the bands. The key is simply the diameter of the cylinder. So let's call scytale our first ancient cipher system, and let's see how we can break it. The study of breaking encrypted messages is called cryptanalysis. With a rail fence cipher, you can simply try a bunch of numbers of rows by hand. So this is called a naive brute force key search. So for example, to break this ciphertext, we would write it over grids with 2, 3, 4, and then eventually 5 rows to find the right key and the plain text. So the first code breaking is a naive brute force key searching, and that means the strength of an encryption system depends on the total key space through which an attacker has to search. So that's how many possible keys are there. So to break a message encrypted with a scytale, I mean, how many keys can there really be? You just wrap the paper around a bunch of different cylinders and call it a day. So scytale versus brute force is our most ancient fight between the code makers and the code breakers. So we skip ahead about 700 years to an encryption system I'm sure everyone has heard of. It uses a substitution cipher, which doesn't just move letters around, but actually changes letters into others. So everyone's heard of the Caesar cipher, and this works by shifting the alphabet by some number, creating a new cipher alphabet, and then substituting plain text numbers with their shifted equivalents. So in this system, the key is the number of the shift. So the good news is that the code makers have a new encryption system, but the bad news is that breaking this is just like breaking a scytale. You use brute force, because there's only 26 possible shifts in the English alphabet. But as the code makers, could this new kind of system give us a new kind of key with a larger key space? So it would take an attacker a lot longer to search through them all. Which brings us to a random substitution. So in this system, you replace each plain letter with some cipher letter, but our key is some randomized anagram of the alphabet. So the good news is you can rearrange 26 letters into 403 trillion possible keys. So this is a huge key space. So even if someone could check it every single second, it would still take them 120 billion years to crack this. And this brings up a really important point to understand about crypto, which is that most crypto systems don't even try to offer perfect encryption, and if they do, run away from them. Most crypto systems are built to force attackers into one of these key searches that just takes so long that it's never going to happen, right? So this key search would take several decades, even with hundreds of thousands of high-end modern computers. But there's a problem here. A key in this crypto system is really complicated and it's hard to memorize, which means it's going to be written down, and when it's written down, that's another way for an attacker to get it. So if we create a random enough key that is easier to memorize, then that would fix this problem. So we'll do this by using a key phrase and then turning that into an entire alphabet. So we start with a key phrase, like Julius Caesar, and we remove any of the duplicate letters. Then we write it and all the remaining letters in the alphabet in order, skipping the ones that were already in the key phrase. And now we have a cipher alphabet to encrypt our plain alphabet. So this is a key derivation function, and you may have seen this in software development. It's a way to turn some source key material into a key that is useful in some system. So now we can encrypt this plain text above into the ciphertext below using an easy-to-memorize key. So we have this easy-to-use cipher up against brute force that would take billions and billions of years to perform by hand and take decades to crack, even with hundreds of thousands of computers. So like all JS conference keynotes, just npm install my module, and all you have to do is use that. You're good to go. But seriously, so this non-shifted substitution cipher was considered unbreakable for about 800 years. And then in the 9th century, Abu Yusuf al-Kindi wrote a treatise on code breaking where he explained a frequency analysis attack. A frequency analysis attack is based on the fact that in every language, some letters occur more often than others. So if you have some ciphertext and you know the plain letter frequency, you can count which cipher letters are the most frequent and guess that they are the most frequent plain letters. If you bring in some more language frequency rules, you give yourself even better guesses, then you apply your guesses to the ciphertext, and you'll see some common patterns emerge. For example here, what's a common 3-letter word in English that ends with H-E? Anyone? The. So you figured out that cipher L is plain text T. Now what's another common 3-letter word that begins with A? R. So now you know that cipher V is a plain D and cipher P is a plain N. So finding part of the key lets you crack the rest of it. So a couple hours later, you can reconstruct the whole key and recover all of the plain text, which means frequency analysis is way faster than brute force. So now the code breakers have the upper hand. This new attack finds the key in hours instead of billions of years. And this attack was considered indefensible for about another 800 years, until the code makers come up with a new crypto system that isn't vulnerable to frequency analysis. So in the 15th century, Leon Battista Alberti devised a polyalphabetic substitution cipher, which uses 2 or more alphabets. So here we see the plain alphabet followed by 2 cipher alphabets. In this system, if you want to encrypt the word secret, you encrypt the first letter with the first alphabet, so S becomes R. The next letter, you use the next alphabet, so E becomes A. Then wrap back up to the first, so C becomes B, R becomes H, E becomes K, and T becomes K. So using 2 cipher alphabets means that the plain letter E became both an A and a K, and the cipher letter K could be either an E or a T. So now the code makers have a system that's not vulnerable to frequency analysis, which means attackers are back to using brute force. But even though polyalphabetic beats frequency analysis, it has complicated keys. This one, go home key, you're drunk. So the code makers need another key derivation function, which is an easy to use, it gives you an easy to memorize key that can use multiple cipher alphabets. And in the 16th century, Blas de Vigenère created Le Chiffre Enchiffrable, pretty bold naming there, a new system that does this. It uses what's called the Vigenère Square, which is this lovely device. At the top is the plain alphabet, and below that, the alphabet is shifted to the left by one space, and below that, shifted to the left again, and so on until the last row is just the plain alphabet again. So to use the Vigenère Square, you first repeat a keyword, in this case secret, across the plain text. In this case, attack from the south at dawn. You encrypt the first plain letter with the alphabet on the row that starts with the first letter of the keyword. So in this case, to encrypt the A in attack, you go to the A column and then go down to the row that starts with the S from secret, and you get an S. Then to encrypt the plain T, you go to the T column and then down to the row that starts with E in secret, so this plain T becomes an X. Stay on that T column for the next T, but move up to the row that starts with a C from secret, and the second plain T becomes a V. So again, the same plain letter has become two different cipher letters. And after you've repeated that for the whole plain text, you have ciphertext that's been encrypted with an easy-to-memorize key and no frequency analysis attack. So now the code makers have this crypto system that's easy-ish to use, and it forces attackers into brute force that would take billions of years. For about 200 years, the Vigenère Square was the apex of crypto systems. But the code breakers aren't going to give up. So this is like the Renaissance, and all the European nobles got to do their super secret spying and mailing letters and having affairs and all that stuff. So the code breakers are actually going to embrace the Industrial Revolution. And in the Industrial Revolution, as early as the 1700s, every European power had a black chamber. And this was typically a state-controlled post office with an assembly line of code breakers who would man-in-the-middle mail. They would open it up, they would copy the encrypted messages, and then send the original mail on its way, and then they would hand the encrypted messages over to a team of code breakers that would break it. And so Vigenère Square was available, but it wasn't always used, because it was a bit complicated. So these code breakers were breaking all the messages that are using the old ciphers, and it was only a matter of time before someone would find vulnerabilities in Vigenère. And you might recognize the person who did this. In 1854, Charles Babbage broke the Vigenère cipher without using any of his mechanical engineering. Babbage just had a keen insight. He realized that while the keyword-based Vigenère Square created those false symbol frequencies, where plain letters become different cipher letters and vice versa, repeating the keyword meant that there would be word frequencies. So for example, if the keyword king is used by Vigenère Square to encrypt the sun and the man and the moon, it would result in this ciphertext. And in this ciphertext, the word the is encrypted as DPR, then BUK, then BUK again. So the cipher word is repeated when it's displaced by some multiple of the length of the keyword. So to break Vigenère, Babbage looked for repeated sequences of letters and measured the space between those repetitions to find the length of the keyword. So for example, in this ciphertext encrypted with Vigenère, these 4 cipher words are all repeated. So we count the spacing between the repetitions, and we see that it's 95, 5, 20, and 120. And since the only common factor of all of those numbers is 5, we know that the keyword is 5 letters long. And once you know a bit about the key, you can more easily get to the rest of it. So at this point, you could go back to brute force looking for some 5-letter word, right? But Babbage had another trick where he actually broke the ciphertext into 5 different chunks. All of the chunks were separated by 5 spaces, all the letters that were separated by 5 spaces. And then he broke each of these with frequency analysis, and then combined them all again to recover the plain text. So now we've got this pretty even race going on between the code makers using Vigenère and the black chambers of code breakers using combination of Babbage, frequency analysis. And now there's 2 major breakthroughs, 2 major tech breakthroughs. In the 1800s, the telegraph is invented, which lets people communicate instantly over large distances connected by long wires. So the first US telegraphs used a single wire system, which is great, but then how do you represent letters or words as electrical signals on a single wire? So this telegraph was invented by Samuel Morse. Morse code is an encoding scheme that turns letters and numbers into sequences of dots and dashes. But Morse code is an open standard, so there's no secrecy in this, right? This is still considered plain text. It just allows you to turn text from a human form into a machine-readable form. So 50 years later, the first radios are invented, and these are great for sending like instant military commands across great distances because you didn't have to lay these long wires on the battlefield. But since the messages are traveling over the air, the enemy receives all of the messages too. So this prompted the need for an equally quick encryption tool, which would then become the most notorious encryption device in history. The Enigma machine was invented by Arthur Scherbius in the early 20th century and deployed extensively and with devastating effect by Nazi Germany. Enigma has an input keyboard, electromechanical rotors, and an output lamp board. When a plain letter is pressed on the keyboard, it completes an electrical circuit that passes through the rotors and lights up a cipher letter on the lamp board. So this is the inside of one of the rotors. The green jumble of wires there on the right are the scrambling wires. Enigma used a series of scrambling rotors that stepped around with each letter. So when you pressed the plain A key, it might travel through the circuit at the top here, resulting in a cipher G. But each time you pressed it, it would advance the rightmost rotor one position. So the next time you pressed the A key, it would follow a different path and become a different cipher letter, in this case C. So when a rotor completed a full rotation, it would advance the rotor to the left, creating all new pathways all over again. So Enigma is this polyalphabetic cipher, but you can use it as fast as you can type. The first Enigma machines used 3 rotors that scrambled 26 characters for 17,000 possible keys. And the key here is the 3 starting positions of the rotors. But the rotors could be rearranged, and 6 arrangements meant it had 100,000 possible keys. So the Nazis used code books with a different key for every day. So if a code breaker could check a key by picking some rotor settings and typing some intercepted cipher text into their own Enigma machine, if that took about 1 minute, then they would have to use 96 Enigma machines nonstop to crack the key by tea time. That's hard, but not unreasonable, because remember, you're dealing with these black chamber industrial era type assembly line code breaking going on. So this is very within reason. But Enigma also has this plug board on the front that makes even more substitutions. And with it, operators could swap up to 6 more letters. And 6 swaps of 26 possible letters meant there's 100 billion possible plug board settings. And if you combine that with the rotors, then there's 10 trillion possible keys. So it would take 38 million Enigma machines to search through them all in a day. And on top of all of that, they didn't even use the day key for all the messages of the day. Instead, they used the day key to send a new rotor orientation for every single message. So the sender would pick ASD, and they would type it twice for integrity checking. So they type ASD, ASD, and that becomes QWERTY. The receiver sees QWERTY, and they type QWERTY on their Enigma machine. They see ASD, ASD. They change their rotors to A, S, and D, and then they type the rest of the message from there. So all of this is meant to minimize the amount of ciphertext that's generated by the day key. So if you're attacking Enigma with those 38 million Enigma machines, you're not cracking the day's messages. You're cracking a single message of Enigma. So Enigma is the culmination of implementing state-of-the-art cryptography with state-of-the-art technology. But as we've seen already, no code breaking is indefensible, and no encryption system is unbreakable. The story of cracking Enigma starts in Poland and the Bureau Szyfro. This is the Polish black chamber where Poland spied on its neighbor Germany. So Poland received an Enigma instruction manual via French espionage from which they deduced the rotor wirings and how the code books worked. And the team to crack Enigma was led by Marian Rejewski. And like Babbage, Rejewski realized that the repetition is a vulnerability in any crypto system. So he focused on the repetition of the 3 letters in the message keys. He saw that when a certain cipher letter appeared first, another cipher letter always appeared fourth, because it was the same plain letter being encrypted the second time by the day key. In later messages, that fourth cipher letter would show up as the first, and then be followed by some new fourth cipher letter, and so on. And eventually, these chains would cycle and start over again. So he didn't know any of the plain text of any of these letters that he's looking at. He only saw that the number of links were cycling consistently. And then he had a brilliant insight. He realized that the number of the links in the chain are only caused by the rotors. So he could split the problem of cracking it in two and concentrate on breaking the 100,000 rotor settings first, which is 100 billion times easier than the full problem. So his team created a cyclometer, which is a device that simulated all the rotor settings of Enigma to record all the possible chain lengths of the cycles. They kept the results in a card catalog system that took a year to finish, but with it, they could intercept Enigma messages, count the chain links in the ciphertext, and then simply look up the rotor settings in their catalog. So they made the world's first rainbow table. After the rotor settings, finding the plugboard settings was easy. Like we saw in frequency analysis, when you have part of the key, you can get the rest of it. So in this case, they unplugged all of their Enigma plugboard wires, they set the rotors to what they knew were the right settings, and typed some ciphertext. They would then see some pretty obvious letter swaps in common words like weather. The R and the W would be swapped. So after the cyclometer, the Polish created more electromechanical machines for code breaking. Their cryptographic bombs could recover Enigma keys in 2 hours. And then in August 1939, Poland smuggled their machines and their research to the Allies, and 2 weeks later, Hitler invaded Poland. So the Allies picked up Enigma code breaking, and they built bigger cryptographic bombs, which were operated by thousands of the Women's Royal Navy Service at chambers like Bletchley Park, where Alan Turing contributed to programmable advancements in code breaking. And inspired by Turing's ideas, Tommy Flowers designed Colossus Mark I, which was completed in 1943 and used 1,600 vacuum tubes to perform operations many times faster than the electromechanical bombs. And so Colossus is regarded as the first programmable electronic computer. So with Colossus attacking Enigma, the code breakers regain the upper hand, and Colossus is searching for and finding these Enigma keys, but it's a lot faster than brute force. It's a new kind of force, like a Jedi force. It's an example of new technology changing the time complexity of some crypto system. So sometimes code breakers come up with new attacks, and sometimes they get hold of new technology. So keep this in mind when we talk about crypto, or quantum. So we've got computer-powered code breaking against electromechanical code making, and the world starts communicating more and more with these computers, so the code makers need to catch up. In early computers like Colossus, electrical signals were not really precise, so it made more sense to only distinguish between two states, on and off, which are the ones and zeros, which we call binary. And like the telegraph required Morse code to turn messages into electrical signals, computers need a way to turn messages into ones and zeros of binary. So there's 2 steps to this. First, we represent numbers in binary. In binary numbers, each place is an exponential value of 2 instead of 10. Then we assign each letter a number. And in 1963, ASCII was standardized as an encoding scheme for turning letters and other symbols into numbers and then to binary for computing. When we get our messages into binary, we can encrypt them at this level of ones and zeros, which is called bitwise. And we could perform any of the encryption ciphers we've seen on binaries. For example, consider this short sentence encoded to ASCII, then encrypted with railfence, becomes some ciphertext of binary. Then you decode it as ASCII, and it shows this garbled result. So if you've ever seen string values that look like this, you're probably looking at ciphertext, improper decoding, or both. So there's also a bitwise substitution operator called XOR, and it receives 2 bits of input, a 0 or a 1, and it outputs a 0 if they're the same, and it outputs a 1 if they're different. So the cool thing about XOR is that the output is a 50-50 chance. It's a digital coin flip on a bit, which is what you need for something like a substitution. So we could perform a substitution using XOR. For example, encode this short sentence with ASCII, encode Julius Caesar with ASCII, then encrypt the binary plain text by XORing it with the binary key, and we get this binary output, which looks like this when you finally ASCII decode it. And so notice, the key was only long enough to encrypt some of the plain text. But we could generate a random key, the full length of the text, so we can encrypt the whole thing. So the operation's the same, the key is just longer. Now, every cipher that we've seen so far has been a stream cipher. That is, it operates on a single digit or character at a time. But we've also seen the problems in these ciphers. Encrypting one plain text digit with one key digit or repeating the key leaks information about the key into the ciphertext, which makes it vulnerable to attacks. So this is just as true for ones and zeros as it was for letters. So this straight bitwise XOR is vulnerable to all the same attacks that we just talked about. So the code makers need a cipher that can better hide the key information into the ciphertext. And in 1971, Horst Feistel and colleagues at IBM published the Lucifer cipher, which was the earliest civilian block cipher. So instead of operating on single bits, a block cipher operates on groups of bits called blocks. And this simplified one, it reads a plain text input and a key and applies many rounds of bitwise operations. So in this example, 16 bits of plain text is first XORed with a 16-bit key. The output is grouped into 4-bit groups and put through these substitution boxes, or S boxes, which are like mappings that turn predefined set of 4 bits into 4 other bits. And finally, the output from that is put through this permutation step, like an anagram. In this example, the whole process repeated 3 times. So altogether, this is known as an SP network. And you can find these kinds of diagrams for all modern block ciphers. They're just designed to maximize the diffusion of the key into the ciphertext. So here's a diagram of Lucifer. And if we were to walk through it, we would take a 256-bit tweet, break it into 128-bit blocks, generate a 128-bit key, break each block. Okay, I'm just kidding. We're not actually going to do it. But if you see these kinds of diagrams, just understand that yes, somewhere in there, you can get down to the ones and zeros. It's just that block ciphers work on so many ones and zeros, it's easier to describe them like this, right? So if you've been doing software for a while, you've probably heard of DES. Anyone heard of DES, Data Encryption Standard? Okay, so DES is a standardized Lucifer cipher with a 56-bit key. That's what it is. So if you ever wondered where it came from, now you know where it came from. The NSA tried to convince IBM to make the key 48 bits because they had a computer big enough to crack 48 bits, but they compromised on a 56-bit. So if they really needed to build a new computer, they could. With DES, the code makers are back on top. So even Colossus is not designed to attack block ciphers that make it quick and easy to perform so many rounds of this kind of permutation. But since computers keep advancing, how hard is it to find a 56-bit key? So with 56 bits of ones or zeros, there's 72 quadrillion possible keys. And in 1978, it would have cost $20 million to build a computer to break that. And the NSA could definitely afford that, but they didn't have it yet. So I'm going to reset our timeline, because we've got a pretty even battle going on. And as we saw with Colossus attacking Enigma, even brute force can still be a problem. So since 1970, every 2 years, the price of electronics has been cut in half and the processing speed has doubled. And very quickly, 56-bit keys are vulnerable to reasonably priced attacks. But one great thing about binary keys, as soon as you add another bit, you get double the number of keys. So with one more bit, you get 144 quadrillion possible keys. Still, you can't just throw a bit into a block cipher that's made to work on 56 bits. You can't just turn it into 57 bits. So right now, Moore's law is helping the code breakers a lot more than the code makers. But the code makers come up with triple DES. So anyone ever heard of 3DES? Anyone seen that? Okay. So triple DES is a backwards compatible way of being able to use a bigger key in DES. So it uses 3 different 56-bit keys in 3 different steps. Encrypt with the first, decrypt with the second, encrypt with the third. It's backwards compatible, but if the sizes are so strict on these keys and on these blocks, you might be wondering, what about messages that are longer than the key size? So how do you use a 168-bit block cipher to, say, encrypt 336 bits of a message? So you apply triple DES to data larger than 168 bits, you need a block cipher mode of operation, which is a big mouthful. But the simplest mode is electronic codebook. And so here you just break the plain text up into blocks that equal the key, and you just encrypt it with the key. But like Babbage and Rajewski found out, you're probably wondering, isn't repeating the key bad? Yes. So a striking example of how this ECB mode leaks plain data into cipher data is if you take this image and you encrypt it with an algorithm in ECB mode, it shows you that this much repetition pretty much tells you what the plain thing is, right? So you're leaking a whole lot of plain data into the resulting cipher data. So the code makers have come up with better modes for better diffusion, like cipher block chaining. So this uses an output ciphertext from one block as input for the next block. And that means it helps diffuse the key so the final cipher data is less obvious. So with triple S and new block modes, the code makers have these techniques that are keeping them ahead of Moore's law. But we still have this nagging problem. No matter how great the encryption system is, how the heck do we come up with these keys, and how are we going to share them, right? In the early days of computing, people did it like they did with Enigma codebooks, where banks would literally like fly people around with suitcases strapped to their arms with disks with encryption keys, right? But as you're building up the internet and it's getting bigger and bigger and bigger, this is a giant pain in the butt. So you can't do this forever. So what the code makers really needed was to solve this perennial key distribution problem. And in 1976, Whitfield Diffie and Martin Hellman published a paper with an amazing breakthrough. So to understand how they solved this problem, you set it up clearly. So two people, Alice and Bob. Hey, we made it to Alice and Bob. So Alice and Bob need to communicate securely. And to do that, they need to share some secret key. But they only have public channels between them because Eve is always eavesdropping. So how can they share a secret with each other without sharing it with Eve? So they come up with what's known as Diffie-Hellman key establishment. And this needs a one-way function, that is, an operation that's easy to perform in one direction but hard to reverse. So for example, it's easy to mix two colors, but it's hard or impossible to unmix them. And in this color analogy of Diffie-Hellman, Alice and Bob agree on some base color, which Eve also sees. Then Alice privately chooses a secret color, mixes it with the public color, and sends her mixture to Bob. Bob privately chooses his own secret color, mixes it with a public color, and sends his mixture to Alice. So at this point, Alice, Bob, and Eve all have the public color and the two mixtures. And now comes the cool part. Alice and Bob each add their own private color to the other one's mixture, and they both arrive at the same shared secret color. But without one of their private colors, Eve can't get to this color. So now we have a way, this is like a shared secret key that we would use for triple S, but to do this on a computer, we need to do this with binary. And remember that a key could be anything that it can code to ones and zeros, so anything like a number. If we use a number as the key, I'm afraid we need to use math. So we're even covering a little crypto math today, because we need to know it to know the quantum threat. In math, we have some one-way functions, and the one we're going to use for Diffie-Hellman is called modular arithmetic, which is also known as clock arithmetic. So for example, to find 46 mod 12, you divide 12 into 46, and the remainder is the answer. Another way to think of this is to wrap a chord that's 46 hours long around a 12-hour clock, and it will end on the number 10. So 46 is a generator, 12 is a modulus, and we say 46 mod 12 is congruent to 10. So this is easy to perform, but it's hard to reverse. And in this form, it's actually impossible because there's so many right answers that could be false positive, just like the random anagram. So it would be impossible for our recipient to know what number we want to use. So we need some way to calculate this with an algorithm and a key, and that key needs to be made up of a secret from both Alice and Bob. So to do this, Alice is going to raise the generator to some exponent and then take the modulus of 17. So the result is going to be 12. But Alice keeps her exponent secret, and she only shares her result. So this equation is known as a discrete logarithm problem, and there's no generalized method for solving this, which means there's no shortcuts, so it's easy to perform in one answer, and it's hard to go back. You would have to brute force the number. For small numbers, it's kind of easy to guess, but not for prime moduli that are hundreds of digits long. But we need to turn that single secret number into 2, and the way we're going to do that might seem a little trickery, but it's actually easier than you suspect. It's what we learned in first grade math. So remember, we learned that addition and multiplication are commutative, so it doesn't matter what order you put the numbers in, it comes up to the same result. So if you put exponents in a sequence, that goes the same way. So if you raise 3 to the power of 2 and raise that to 3, you get 729. But if you raise 3 to the power of 3 and then raise that to 2, you also get 729. So this is what we're going to use. So first, Alice and Bob publicly agree on a generator and some prime modulus that everyone can see. Then Alice picks a private exponent and sends her result to Bob. Bob also picks a private exponent and sends his result to Alice. So now Alice, Bob, and Eve all have the generator, modulus, and the results, and we do the cool part, where Alice raises Bob's result to her own private exponent and gets 10, and Bob raises Alice's result to his own private exponent and gets the same number 10. So they actually did the same calculation because if you go back to their original forms, they both raised the generator to both of their exponents just with the exponents in a different order. But changing the exponents doesn't change the result. So this breakthrough to establish a shared secret over public channels is the foundation of public key cryptography. And it's really hard to overstate how important public key cryptography has been to the internet, computers, and all of modern life. So with Diffie-Hellman, you can establish these shared secret keys that you can then use in an algorithm like triple DES. So with this, the code makers have basically brought us into the modern steps of cryptography. So we have a way to establish secret keys with anyone on the internet and an encryption algorithm to use them. And we have modes to use the keys on any message. The only way to attack all of this is with brute force. So I want to try to blow your minds a little bit now as we're getting close to the end. We've gone from a scytale to Diffie-Hellman triple DES with cipher block chaining mode. So how many of you have ever crossed something that looks like this? And you were like, what in the heck is all of that? If you're in your browser network panel, you actually know most of this. So this is a TLS connection that's using Diffie-Hellman for a secret key, then using triple DES with cipher block chaining mode. So hopefully you see that all of this modern crypto stuff was developed sequentially in steps. Okay, so what's this RSA part? It's arguably the most important, and it's the part with a vulnerability that a quantum computer could exploit to ruin the security of the whole internet. So with Diffie-Hellman is great for coming up with keys, but if you used it for everything, you'd have to have separate keys with every single person you want to talk to. So in 1970, James Ellis developed an idea for public encryption that was more like locking and unlocking messages. So instead of making a new keys with everyone, Alice could have a single key for herself and publish some open lock for everyone else. So anyone could lock messages to send to Alice, and only she can open them. So Ellis never found a mathematical solution for this, but in 1971, Clifford Cox came up with a trapdoor one-way function to do this. And a trapdoor one-way function is easy to perform, hard to reverse unless you have some secret knowledge. So Cox needed to come up with a math function that does this. So in the 4th century, Euclid showed that every number has one prime factorization. That is, there's only one set of prime numbers that make up that can multiply to equal that number. And prime factorization is a hard problem. So if you multiply two large prime numbers and get some giant result number, it would be hard to get back to the prime numbers if you only know the result. But a trapdoor for it is, in the 18th century, Leonard Euler defined the phi function, which measures the breakability of a number. It tells you how many numbers are less than the number that do not share a factor. And in this case, phi of 8 equals 4. So calculating phi is also a hard function except for one kind of number. Can you guess what that one kind of number is? So prime numbers are easy to calculate because it's just 1 minus the prime number. So Cox took the phi function and multiplied the phi of a large prime number times the phi of another large prime number. And that means the resulting number is almost impossible to get back to the two primes that made it. So Alice picks two prime numbers, calculates their product in phi. She picks a public exponent and calculates some decryption number. Then she hides everything but her exponent and result, which is used as a modulus, and she can publish these to anyone and everyone. So with this, Bob can encrypt a number with Alice's public key, and only Alice can use her private key to decrypt it. So Eve would need to find Alice's prime factors to decrypt Bob's number. So how hard is that? Well, multiplying numbers is easy and stays under a second, even for really big numbers. But factoring numbers, while for small numbers, stays under a second. But as the numbers get larger, there's this runaway exponential effect, where finding the prime factors gets exponentially harder and eventually takes hundreds or thousands of years to do for big enough numbers. So this discovery was immediately classified in Britain by the GCHQ, which is like their NSA. But a few years later, it was rediscovered by Ron Rivas, Adair Shamir, and Leonard Adelman, which is why we know it as RSA. This is the most widely copied piece of software in the world. So the code makers have a way to give anyone on the internet a pair of encryption and decryption keys and an algorithm to use them, and the only way to attack it is with brute force. But even if Bob can encrypt messages to Alice, there's still a problem. How does Bob know that it's really Alice's public key? And to establish this trust, Alice is going to get a public key certificate. So she submits her public key and some identification to a certificate authority. The authority signs it with their own private key to make a signature, to a signed digital certificate. And now when someone like Bob wants to make an encrypted connection with Alice, she presents them with her signed public key certificate. So for example, close to my heart, this is the site that I work on, monitor.firefox.com. So if you look, there's our RSA exponent and modulus right there. So look, all that math, it's right there in the internet, powering all the sites that you use. And this is signed with an RSA private key of DigiCert, which is our CA, which is itself signed by a root DigiCert private key. And these root private keys are usually held like in very physically restricted locations. They're not connected to the internet, they're offline. So cycling them would be a disaster. So the public key matching that root private key comes preloaded on almost every operating system in the world. So because brute forcing the prime factorization of that private key is really hard, devices trust all of these connections that are signed with all of these root private keys. And this is something that a quantum computer could attack. So in 1980, Paul Benioff proposed a quantum mechanical model of a Turing machine that could leverage quantum superpositions. And basically, instead of having bits, a quantum computer has qubits that can be both a 1 or a 0 at the same time. And if you think you understand that, you don't. So everything about quantum computing, if you ever go through it, it basically says, if you think you understand this, you probably are doing it wrong. But in 1994, Peter Shor invented a quantum algorithm for prime factorization. So we're not going to go into it, but like Kindi and Babbage and Rajewski, he saw that if you could break part of the key, you could get the rest of the key. So his algorithm breaks the prime factorization problem into two and then uses quantum superposition mechanics to solve one part of it and then grab the rest of it. So if a quantum attacker can solve the prime factorization problem for, say, DigiCert's root certificate, they could generate their own public key certificate for any domain in the world. And they could sign their own fraudulent certificates and hijack secure connections from any client to any server. So this is bad. Public key certificates are also used in all kinds of integrated circuit chips, like your credit card, or the Department of Defense has a common access card, like how you get into DoD buildings. So the bad news is a quantum attacker could basically forge digital signatures and attack most of modern technology, right? The good news is that all of these public keys are using 2048 bits of RSA. So to break that, you need a quantum computer with over 4,000 qubits. And the largest quantum computer to date is Google's quantum computer that's 72 qubits. And it would take, we're still many, many, many years away from a quantum computer that could break the RSA keys of 2048 bits. In addition, the National Institutes of Standards and Technology is already in the process of standardizing post-quantum encryption standards. So these are not vulnerable to Shor's algorithm. And in their timeline, they anticipate that they'll standardize and deploy these before a quantum attack is actually reasonable. So where does all this crazy quantum attacks and defenses leave us as software developers? So I wasn't joking when I said the key to encryption is the key of encryption, because in reality, with all this fancy cryptography, math, quantum mechanics, it's summed up in a classic wow, we're getting into rock right now. XKCD comic. So in some crypto nerd's imagination, their laptop is stolen, but it's encrypted with 4096-bit RSA, and the attackers can't build a computer that's big enough to crack it. And that's both the strength and the weakness of cryptography. So throughout history, code makers are forcing code breakers into key cracking attacks that would take too long to complete. And while a quantum attack against RSA is like fast and impressive, consider that it takes a quantum computer to defeat this much JavaScript. And we've got to JavaScript at a JavaScript conference. So this is implementing RSA in JavaScript. So with this much JavaScript, you need a quantum computer to defeat this. And this is what I love about cryptography. Security is usually an unfair fight between the attackers and us defenders, because the attackers only ever have to find one vulnerability for all of our security to go crashing down. But the math of cryptography actually forces the attackers to move elsewhere. They cannot attack the math. Or if they do, they have to build a quantum computer to do it. But the strength is also a problem, because what actually happens is that since you force the attackers into those other attacks, what really happens is they're going to drug the victim and hit them with a $5 wrench until they give up the password. So there's really only two main points to take away from this. Don't invent your own crypto. So as modern software developers, we have an embarrassment of riches when it comes to crypto libraries that we can use, right? Use the popular ones. Use the well-tested ones. Do not invent your own crypto. And secondly, when you're using those crypto libraries, mind your secret keys. So all the fancy crypto in the world can't help you if you let your secret keys out, if you give away your password, or if they get hijacked or stolen somehow, right? So don't paste your secrets into a GitHub repository, right? So just yesterday, NordVPN admitted that they were breached and that the attacker stole a private key. And with that private key, they could go back and either fraudulently present themselves as NordVPN or go decrypt NordVPN traffic. So there it is, right? Up to yesterday, and the biggest attack, the biggest news of the day is still that private key is getting out there. So that's it. We went from ancient to quantum cryptography.